All right, so let's now talk about something very important. I think just about your, okay, tomorrow is a drop deadline. Hopefully everybody stay. But I'm going to return the result. I'm still expecting the TA to get back to me about a certain grading result, the final phase. They should really give back to me by 8 p.m. tonight. And then after that, I'll maybe take the evening, possibly tomorrow morning or early afternoon to do some final processing. So I'll release the marks about your test one, both the programming and the E-class at the same time. So definitely before the drop deadline. So if you have to make a decision, you'll definitely get it in time. And so guys, please notice that I already put it in the E-class announcement just about your assignment number 2 and test number 2. Basically, they have been shifted by 1 week, but the weights is the same according to the syllabus, and also the duration and also the time is going to be also during the lecture time. So it shouldn't really cause any inconvenience, but let me just mention that once again. So if you look at the semester calendar, which has been updated, okay, let's just see where we are. All right, so we are now here, November 3rd, right? So tomorrow on the 4th, I'm gonna give back to you the test 1 result. And then next Wednesday, I'm going to release your assignment number 2. And then you'll be given about a week to do that, and similar pattern. So next Wednesday on the 19th, beg your pardon, the week after, right? If you look at the calendar here, it's going to be due in a week, but on that particular Wednesday, we can potentially maybe do some review just on the lecture part because we're going to cover some new algorithm and some new implementation strategy. So there will be some stuff that we can clarify in the review session. And then also in the tutorial, we can go over the programming part and the written part for your assignment number 2 as well. Okay, so next Wednesday, 12th, you can expect the release of your assignment number 2. A week later, they will be due, and they'll give you the solution. And your test number 2 will be on the 24th, not 17th anymore. All right, so that's something I kind of made an announcement on the E-class. Okay, and then I'll try to look at maybe how you guys did. You know, I've still got to look at everybody, the marks. I haven't got everything just yet. So I will see if I can balance a bit, maybe for test number 2. We'll see. Okay. All right, questions? Anything just unclear? All right, so today I want to finish off about breadth search. We can maybe do the part of the complicated example together, and then just to make sure you're feeling comfortable about the breadth search, and then we can make some insightful observation as well. And there's also some interesting comparison we can make between depth search and also breadth search, especially about cross edges versus back edges. So these are the 2 things we can also compare. And then after that, I would like to talk about the second implementation strategy for the graph, which is called adjacency list. Okay, it's a little bit more like an extension to the edge list, which you guys study for assignment 1 and also test 1. And if time permits, we can also start talking about the weighted graph, because the next algorithm I would like to talk about is a so-called Dijkstra shortest path algorithm. That would be nice for us to go over as well. That is quite a sophisticated one, so that's going to take us maybe 1.5 lectures. We'll see. All right. Okay, that's roughly the plan. And then after that, we'll talk about other algorithm after the test. Okay. So let's now take a look at, right here, right? So everything I just said. Okay. Let's now take a look at what we said last time in the lecture, okay, very quickly. So it's mainly just about that breadth search. Let me just go directly to the breadth search. Of course, we spoke about how you can adapt the answer you get from depth search, and then to see how you can adapt it to answering various graph questions, right? So that's something we spoke about 2 weeks ago. And then I want you to pay attention to this particular question over here. How do we know if there is a cycle in the graph? If you're trying to do a depth search, you can easily see if I have a back edge. In that case, I know the path leading to that back edge is going to give me the cycle. So this actually is true no matter your graph is directed or undirected, right? So we didn't really emphasize that, but that's something I would like to do a comparison. And we're going to ask a similar question later today after we have done a little bit more example on the breadth search. If we ask the same question over here about if I do a breadth search and there's something called the back edge, if I have a back edge, does it always imply I have a cycle in the graph? I can tell the answer right away, not necessarily always. So that's something we'd like to see a little bit more. Okay, I'll give you examples, so don't worry. I want to give you just like some look ahead, some heads up. All right, so please go over the basic questions here. So these are really kind of showing that depth first search and breadth first search later. They are the foundational ones. You can always pick up which one you want to do and then build something from there. And that's something we did from last time, but I'm going to do some another example from scratch so we can see. Because in that particular example, there is no cycle. So there is no, for example, like a back edge like this. So it's not exactly like a very representative example for breadth first search, but we'll try that today. So for breadth first search, you just have to remember you're actually going to use a FIFO first in, first out queue as opposed to stack to really keep track. We'll see exactly today. Okay? And then it's very important to really notice this particular keyword. The way you're going to somehow mark the edges in the breadth first search, you somehow try to divide your graph into different levels. That's something we'll see as well. So for example, let's say this is a starting vertex over here. So let's say this is level 0. And then after doing level 1, we're going to do for level 2. And then we do level 3, right? Just level by level. But if your graph actually has a cycle, that means you're still doing level by level. It's just that you will have some back edges between vertices at the same level. Right? That's something we'll see today, so don't worry. I just want to give you some heads up quick. Right, you can definitely go over the principle about breadth first search. And then today, which I want to start with just some example, just to see. All right? Any questions just about the basics for breadth first search? Okay, yeah, in some ways rather, I wouldn't say similar to depth first search, but just another way to systematically visit all the edges and vertices in your graph, just a different way. Okay? And then we talk about there are two kinds of edges. Discovery edge has the same meaning as before, like in the depth first search. Whenever you're basically following the incident edge from the particular vertex, you're visiting a vertex that has not been visited earlier. In that way, that'll be discovery edge. And then we got another edge here. We call it cross edge, not back edge anymore, right? Cross edge. Cross edge simply say, this is level 0. This is level 1. And then somehow I have a vertex connected with another one at the same level, right? That's called the cross edge, right? And that's something we're going to see a little bit later. A question?
Yeah, so with the discovery edge, the example shows only the one vertex, giving like the new discovery edges. What if there's another vertex that points to the same vertex that this A is pointing to?
Okay, so are you, okay, let me just be sure. So here, are you suggesting we add one more vertex?
In the same level as A, that's pointing to the same things as A.
I see what you mean. It's a very good question here. So that's something, for example, let's say you got another one over here. Let's call that maybe X, for example, okay? So of course, I can maybe try to make this example maybe next time to just go over it with everybody. But you follow the same principle. So now in this case, how many incident edges does X have? You got B, C, D, and X. So the way to go about it is you got to go for alphabetic, let's say. That means I'm going to go for discovery, 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 and discovery. So all these 1, 2, 3, 4 vertices will be considered as level 1. Okay. You're just adding one vertex to level 1.
What if there's like in the same level as A, the X is also pointing to?
Okay, you might be thinking that, okay, let me just do this. Okay, let me answer properly. If you actually got, let's say, let me just try here, okay? It's a good question. So B, C, and also D, right? You're saying, what if I have another, okay, let me just use this same, slightly different, right, let's see here. Let's say we start with this, okay? Visually, you might be thinking, this X over here is the same level as A. And these 3 are like a lower level. You might be visually, but that's misleading. Yeah. Because computationally, I mean programmatically, which you will try in A2, okay? When you actually start with A, what you do is, this A here is considered as level 0. Anything that's reachable from A by a single discovery edge is considered as level 1. In that way, you can go either here, 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 and here. So the way to see this, okay, is this. Think about this A itself right here is like a level 1, sorry, level 0. And then all these together right here is more like a level 1. I hope that answers your question, right? It's a very good question. And then actually the second example I want to do today about breadth search, I'm going to take that your assignment number 1, that kind of big graph, and that we'll try to do a little bit of that. You will see sometimes when you actually divide a level, it may not be strictly vertical. Sometimes you may want to go a little bit diagonal, like that. Okay, good. Okay, we'll revisit this with more concrete example. Okay. All right, so we're going to see how exactly we can mark the discovery edge and also cross edge, right? We'll see. And then a very important comparison for us to do is to compare cross edge and also back edge back in the depth search to see how they are somehow correlated with cycle. Okay, that's something we'll do. Okay, so why don't we start with one example, simple one. Let's do a warm up together. Okay. Oops, sorry, right here. Okay, there we go. Okay, let's say this one here. And of course, any of the vertices could be the starting vertex for breadth search. Let's say we start with A, just simple. Okay, let's do this together. Okay, let's say we start with this one here. Okay, so this will be the start of breadth first search. And let's kind of follow the similar style in my assignment number 1 solution. Okay, let's try to keep track. Of course, there's no push or pop anymore. It's in queue and DQ, right? We're using a queue. So let's say we do a table here. Oh, no, it doesn't need to be this wide. Like here, all right? And then a table. And then we talk about in queue. And also DQ. We're going to see the order, right? We're going to keep track from top to bottom. And then let's now also consider there is a queue right here. How exactly you want to visualize the queue you're operating with is completely up to you. I just prefer horizontally, for queue, and vertically for stack. You don't need to follow that as long as you know how things will work. Okay, so here I'm assuming that over here is the front of the queue. And this will be the back of the queue. All right? And then, so we start with putting or in-queuing A. So we put A right here. And we only label the edges to say the chronological order of marking the edges like before. Okay, so A here, that's good. And that's the first one to be in-queued. A. All right? So now we're going to go over the incident edges. So now we got to, you think about A here is like a level 0. Let's now do that distinction right away. So this is level 0. Level 1 is going to be all the edges that's going to be one edge away from A, which means all the vertices that can be reachable by the incident edges of A. Then it's considered level 1. Okay, let's see. Okay. So you can see from A here, we can definitely reach out to B. We can reach out to B. Let me make it a bit thicker. How about that? Okay, we can reach out to B. We can reach out to C. And we can also reach out to D. Okay, so the numbers over here is going to be alphabetical, right? So let's say, so we're going to put 1 here, 2 here, 3 here. So this is the very first edge being marked. And there's a second one, there's a third one. And each time you're marking an edge, it can be either discovery or it can be cross edge. All right, so let's now in-queue them carefully. So I would say exactly how you trace it, sometimes to be 100% very cautious, you may only want to do one label at a time and finish everything and then go for the other one. But if you want to do multiple things at one go, it's okay, as long as you're confident enough. I'll leave the choice to you. But in this case, since 1, 2, and 3 are at the same level, so maybe I can do it. So what I would do is, I got in queue over here, basically B, C, and D, alphabetical order. B, C, and D. So I got B, C, and D. And I can also make some notes over here. So B here is by the edge marked as 1. C here is by the edge marked as 2. And D is by the edge marked as 3. Right? Very clear. All right? So we say that up to now. Let's also see some correspondence on the Q. Up to now, oh, sorry. So let me just make a dash. So this one here, and also this one here. All right? You can think about this one here, A alone is level 0. I'll just say L0. And then B, C, and D are all level 1. Okay? So you can think about this. Just because the way we kind of organize the graph, so it's just perfectly just vertical when we do the levels. But we will see sometimes it may not be the case visually. Okay? Just don't be misled. Okay? So this one here will be level 1. All right? So now we got B, C, and D, right? You can think about right now, A, B, C, D. They have all been visited. And it is important, I'll write a principle here. When should you DQ a vertex? Okay? Very similar to when you have to pop a vertex from the stack in the case of depth first search. I'll write the principle here. So you have to DQ a vertex when all its incident edges have been marked. Right? As soon as it's the case, you should really DQ. All right? 1, right here. So you can see that here, A here has already marked 1, 2, and 3. So A can be DQ'd. Right? So here I can simply get rid of A. So DQ A. Right? Follow so far? Okay. Just got to remember, when you actually do this exercise here, you got to be very systematic about how you want to follow the step, right? We'll try to do one, and then I'll do the complicated one partially, so you can try to continue, and then we can maybe go over the rest, maybe in a tutorial on Friday. Okay, we can do that. Okay, let's continue. So you can see A is gone. So now, where is the new front of the queue? B here. So let's go for B. So basically, this is from level 1. Now we want to reach out to level 2, right? For B here, alphabetically, you can go for C or E, right? When you go for C, it's a cross edge. C has already been connected by some previous discovery edge. So that should be a cross edge, right? So this one here is going to be a cross edge. And I'm going to mark it with a number. So that will be number 4. All right? So no InQ, no DQ should be done. All right? And then the next incident edge would be for B to reach out to E right here. Right? That one there is going to be discovery because E has not been visited so far. So that one there is going to be number 5. So I'm going to InQ E. Okay, InQ E right here by edge number 5. All right, like that. Okay. You can think about what we are starting to build is this particular one. We're going to see it's going to be level number 2. Right, that's what we're doing. Okay, we're reaching out from level number 1 to level number 2, level by level. So now you can see as far as B is concerned, we have marked both edges already. So B can be DQ'd, right? So what we do is we're going to move B away, okay, like that. The next one, the front of the queue will be C, still in level 1. So we're still trying to reach out if possible. So here for C, right here, the front of the queue, we can go this way or this way. Alphabetically, we should go this one first and then followed by this one, right? But this one here, discovery or cross? Cross, because it has been visited already. By the way, cross edge doesn't need to be like a horizontal, right? Sometimes it can be vertical, right? Very good. Okay. So let's now finish that. Okay. So it's going to be cross edge. Okay. So this guy here is going to be number 6. So guys, if I do make some mistake, please let me know. Okay. Okay, number 6, and then we're going to go for number 7, which is going to be another discovery edge for C. And that one there is going to be 7, which will correspond to incoming F. And then F right here. And that one is by the edge labeled as 7. All right. And now, as far as C is concerned, we have marked both incident. We have arc 1, 2, and 3, all the incident edges. So we can DQ it. Oh, I agree. Thank you so much, guys. Appreciate that. Don't make the mistake like me in the test, please. Okay. So that one there. Absolutely. So that one there is going to be number. But I got to be careful here because it's going to go for alphabetical order, right? I think you guys are completely right. So let me just be careful here. So let me just change that. Okay, so let me just do it again. So now for C over here, we should really go for this D, E, and F. We should follow that order, right? So we should really go for number 6 over here, and then number 7, and then number 8. Okay, so only number 8 will actually lead us to F. Right here. All right. So now, as far as C is concerned, we have marked all the 1, 2, 3, 4 edges. We can DQ it. All right. So now we can DQ C. All right. And the next one will be D. Right? Right here. So that's the last vertex to consider in level 1. But we cannot reach out to any new nodes, really. We have discovered already all the 2 nodes at level 2, which are E and F. So now let's do it. So now only this one. That's going to be a cross edge. So that one there is going to be like that. Okay. So it's going to be number 9. Okay. So D is gone. So D and then to D here. And now you can think about right now we have got all the level 2. So let's now put a mark over here. We got all level 2 right here. Level 2. And then from there, can we reach out to any like a level 3? No, we cannot. We're done, right? So you can think about what's going to happen is we're going to go for, let's say, E here, E here. All the 2 incident edges have been marked. So remove it, DQ it. And then F, also, both incident edges have been marked. Also DQ it, right? Just follow this order, E and F. So E, F, and F. In this case, it just happened that A, B, C, D, E, F, A, B, C, D, E, F. We might see something a little bit different later. All right, so we have done with this. And this one here is actually, again, a spanning tree for breadth-first search. We'll talk a little bit more about minimum spanning tree a little bit later, but for now, let's just compare with the depth-first search. So after you have done the breadth-first search, the discovery edges are going to form a spanning tree. Josh.
You sort of like associated some of the edges with particular levels, like 1, 2, 3 is level 1, 5, and 8.
Oh, you mean for the edges? We don't normally do that.
Okay.
You want, what can think, there's a good question here. You definitely want to associate the vertices as the different level. Like this will be left. Yeah, it's more like a distance, exactly, just by the distance from the starting vertex, exactly. So level 0, level 1, and level 2, right? I can write it down. It's a very good insight as well. Think about level 1 are all the vertices 1 edge away from A. So for B, C, and D here, only one edge away. For E and F, they got 1, 2, 1, 2, 1, 2, and also F here, also 1, 2, right? 2 edges. You can just follow the discovery edges, okay? And similarly, you can, I will just write down just for completeness, okay? For level 2 over here, so these are all the edges, vertices 2 edges away. Vertices 2 edges away from A. Okay. What about the edges themselves rather than vertices? So you can see this cross edge go from B to C at the same level. This one here is C, and then it's going to go from C to E to the next level. Right? So these are the 2 possibilities. Is it possible to have a cross edge to go from one vertex to a previous level? Okay, let me write down what we know already, and then we'll put that as a question. All right? So I'll put it here. So think about this is like a star and star, star. Star here. This relates to a cross edge connecting vertices at the same level. Let's get something that we know for sure, and then we get to that question at the same level. Okay, star, star over here. That's an example of a cross edge connecting vertices at the next level. What level plus 1, basically? Because that one there, that particular vertex has already been connected by some previous discovery edge. So it's already been visited. So now the question is it possible, apparently we haven't seen any example like that. Is it possible that, let's say, hypothetically, I'll do some annotation here. Is it possible at this point, this particular edge has not been marked just yet, but somehow from C here, we can have a back edge back to a level that's -1. Obviously not, right? Because that edge over there, if that one's kind of incident on A, we would have discovered C already earlier. So there's no way you can actually have a back edge, you cannot have a cross edge that will go back to the earlier level. All right, very important, all right? I'll write it down, okay? On the other hand, you want to say, I would say put star, 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 all right? Star, star, star. Not possible to have a cross edge linking back to a previous level, because that edge would have been the discovery edge, discovering the current level. All right, that's something you want to also think about. All right, so we got to talk about the different scenario, right, for cross edge. Yeah, that's good. Yeah, the question from George was really nice, so I was able to make some insight here. That's nice. All right, so I would suggest that you guys can also give it a try, like before. So you basically can have, some exception about like the incident edges order. Give it a try on the using a queue and just do the breadth first search, right? You can do 1 and 2 variants. Okay, that's an exercise for you. But I would suggest for today, let's do a little bit of the complicated one. That's a graph you were given on assignment number 1 to do depth first search, right? So why don't we take this graph over here and try to somehow do a little bit of breadth first search. May not finish the whole thing, but at least enough so we can see a little bit more insights. That can also show to you the way you divide the levels of the vertices into 0, 1, 2, 3 may not be exactly horizontal, vertically, as one of your fellow students was pointing out nicely. All right? Okay. Let's give it a try on this. Okay. How about we just do about maybe 5 to 10 minutes, just get enough done so we got some insight to make, and then you can try to complete the rest. And then we can finish that off maybe on Friday when we do other exercises in the tutorial. Okay? Let's say we still start with A. And of course, in preparation for your test 2, you may also want to try to start with a different vertex just to see how the breadth-first search might go like. I can give you one exercise maybe for assignment number 2 just to try. Okay, but let's try with the A here. Okay, so we start with A. You can see somehow we didn't really lay out the graph more like a tree. It's more like a chessboard, like a grid, really. So now the way we're going to divide, let's do something right away. You can see that A itself is level 0. All right? I'll say L0 right here. Okay? And then let's now try to trace a little bit. So we already assume it's going to be follow the order of alphabetic, right? Let me just get rid of this block over here just to save some space. Okay? And then let's now try to lay out a table that we're going to fill out gradually. Okay, I might need all the way to here. Okay, let's see. So let's keep the InQ and also DQ. And of course, we start with A, right? That's the starting vertex. And then let's put our Q right here. Right here. Okay, keep it long. Okay, and then this is going to be the front of the Q. And we already got A inside. Okay, so A is just visited. So we now in level 0, there's only one node, only one vertex in level 0. Let's now reach out to level 1. And the way to reach out to level 1 is by the incident edges for A. So we're going to do basically this one here. If you follow alphabetically, right, it's going to be B, followed by E, followed by F. All right, so let's be careful with the label, right? So it's going to be 1, 2, and 3. All right. So what we have is we got basically B, and then E, and then F. So let's put a label here. It's going to be 2 here, 3 here. Oh, I beg your pardon. It's going to be 1 here, 2 here, and 3 here. Okay. Similarly, we got B, E, and F. I might just repeat the label, but you can keep track. 1, 2, and 3. The labels may not be consecutive. That's something you definitely see, from assignment number 1. Okay, so these 3 nodes are the level 1. And now we can see right away the way you're going to perceive it like a level is not exactly like a horizontal, right? So now you can think about like this. Oh, let me draw a little bit better. Like that. Okay? So B, E, and F, these are the 3 nodes that are in level 1. So it's going to be B, E, and F. So now I think this example here, you can see what you asked me before, just about, for example, let's say for B, it might look like A and B should be at the same level, but they are not, right? Because of the incident edges connection, right? Okay. Okay, so what about we do a little bit more, okay? And then we take a short break. All right, so now we got B, E, and F. So as soon as we reach out to B, E, and F, A is now done. All right, so we can now DQ A. So we're going to actually get rid of A. A is DQ. And then we're now going to look at B right here. The first node in level 1. Okay? And for B here, we can reach out to either C or F. Right? Either way. So let's now either we go for 4 over here, or we can go for 5 over here. Only 2 incident edges, alphabetic, C and then F. Apparently, C here is going to be a new node we haven't visited before. So this will reach out to level 2. And this one here is going to be cross edge. Now you gotta imagine this, right? You can want to think about here, because B and B to F, it looks like B is going lower to F. Yes, visually, but that's misleading. But what we're really doing is we go from B at level 1 to F also at level 1. So that's a typical cross edge. We're still really going from one level to the same level. Okay? I can make a very quick notes for you. Star. Okay? You can say, though organize vertically, vertices B and F are at the same level. Okay, very important insight, right? Okay, like that. All right, so we got C. Let's put C here. So we definitely got C. And then C here is by number 4. All right, over here. But if you like, we can also divide the levels. You can think about here, we got level 0. And then here, we got level 1. All right? And now, as far as B is concerned, we got C and F. Well, these 2 edges marked already, so B can go away. Okay, B can go away. And then we can put B here. All right? And of course, you can put a label here. Okay? C should really associate with label 4. All right? Next one. What's the front of the cube? E. Right? Let's go to E. E is just the second vertex in level 1 that we want to use to reach out to the next level. Right? So here, for E here, we can either go for F or I, alphabetic. Right? So let's now label them first. So we got up to 5. So now we can go for either 6 or 7. Right? 6 or 7. And for 6 over here, you can see that one there, obviously, is a cross edge. Right? Same level. And for I, it's going to be a new level right here. I. Okay? The same level as C. Right? Same level. So I'm going to put, going to enqueue. That one there is going to be I. And that one there will be of label 7. All right? So now I can, as far as E is concerned, I have covered both incident edges. So E can go away. Okay? I'm not done with level 1 just yet, because I still got one more. Right? You can see I got one more vertex, which is F. But that one doesn't seem to be making any new contribution, but we're going to finish that procedure-wise. F over here got 1, 2, 3, and 4 incident edges. All 3 of them have been marked already, so only one here is outstanding. So what I will do is I'm going to do number 8. But that one there is not discovering anything new. It's discovering I. Yes, it's in a new level, but that one has been discovered already previously. So what I will do is I'm just going to do right here, number 8. Okay, so after that, also you can see as far as F is concerned, also is done. So basically we can also remove F. So I should really put E and F. Just be careful, right? Sometimes you might somehow focus too much on one end, you forgot to update the table, right? Just be careful, okay? So far we have done with level 0 and level 1. So what you're going to continue is, you want to continue from here, from level 2 nodes, to see how we can reach out to level 3. Okay, that'll be an exercise for you guys. Okay, let me write it down, and then you can try. And then we can continue from this maybe on Friday, okay? Or Wednesday, either way. So here, let me make a very important remark over here. So this is the next step of the BFS will be go over each vertex at level 2. And let me also visualize the level 2 right here. Okay, level 2 contains C and I, right? It's a little bit like this, right here, all right? So that one there is level 2, all right? C and I, and of course they have been visited already, C and I, all right? And then see how we can reach out to level 3. And reach out to level 3. Okay, next step. Okay, give it a try, and then we can go over the solution maybe on Friday. Okay. All right, any questions about the breadth first search, just about algorithm-wise, right? So I think this will be a nice exercise for us to do, assignment 2, breadth first search. But for assignment number 2, we're not going to touch the edge list anymore. We're going to try something different. Okay, then you can get some variety for assignment 2. All right, why don't we take a short break, and then we'll continue. Okay, so let's do. I think our exam has been also scheduled. I think it's pretty late. Is it December 17th, right? Yeah. So we can definitely schedule some review session for you, at least 2. I think we can definitely do that. We'll maybe do some survey just to. I presume it might be the last exam for all of you. I would presume, maybe. Okay, so we can definitely work around your schedule to see. All right. Okay, so on the slides, we're basically done with the basic breadth first search about marking the edges, and then we got the example there that we did. And also this particular one, of course, that's actual solution. I try not to peek on that, right? You can actually finish the solution yourself and try to how they will work. Right, so let's now take a look at slide number 46 and 47. So these are just the stuff that we want to go over just to see about the graph question that we can answer for breadth first search. Right? I'm just going to talk about both of these kind of together. Okay, so you can look at the slide as well, 46 and 47. Right, let's just go over here. Okay. All right, I'm basically asking the same questions as the depth first search, the same list of questions. So the conclusion I can tell you right away is for all the questions here, for all the questions except for the last one, you basically have the same, almost identical answer to that, except for the last one. But for the last one, I'm going to talk about it separately. That one is definitely worth our attention to compare. Let's talk about them very quickly. So again, but Josh can correct me if I got this one wrong. So hopefully that's okay, right? Tell me. So let's say we got a graph over here. We got a graph here. And then let's say we got 2 connected components, 1 and 2, right? So it's not connected. So that means if we want to really somehow find out a way to really visit all the vertices and edges, we have to do exactly 2 breadth first search, right? Similar to depth first search. So let's say if somehow we start a first depth first search from here, and we start a second breadth first search from here, and we're going to get their markings for the edges like that, right? So that's very similar idea for depth first search. Okay, let's now try to answer the question accordingly. How do you find a path between U and V? Similar. Basically, you keep track of U, start from U, and then as soon as you encounter V, you know that somehow you can maintain the path. Similar. So here we can start breadth first search from U and then maintain the path until V is encountered. Of course, if V is never encountered from U, being the starting point for breadth first search, that means there's no path, right? Similar. I think maybe potentially maybe for assignment number 2, I think I can let you guys definitely try the breadth search, and then we can try maybe 1 or 2 methods that's going to be based on the result for the breadth search, so you get some idea about how to adapt either breadth search or depth search into some graphing problem. Okay, we can give it a try. Okay. I think that'll be a nice hands-on experience for you. All right, second question. Is it reachable? Well, similar. Okay. Again, you start the breadth search from U. Is V ever encountered? If it is, there's a path. Otherwise, it's not reachable. Is V ever encountered? Okay, that's the question, really. All right. So now, how do we find all the connected components of G? Apparently, you have to, well, anybody would like to give it a try intuitively, right? So now, rather than doing depth search, we want to do breadth search. We want to somehow find out all the connected components. Josh, go ahead.
I'm assuming it's the same as depth
Yeah,
search.
yeah. Maybe help us refresh a bit. How would you do that?
You do the breadth search on like each of the connected like you the number of times.
Right. You basically, yeah, you got to keep doing the breadth search until all the vertices have been reached, right? Okay. So this one here, I'll try to see maybe I can adapt this to assignment question for you guys to try. Okay. So basically, you're going to say, keep doing breadth search until all the vertices are visited. How about this? Let's now sketch this very quickly, right? I normally don't like to sketch like a pseudocode because it's not really precise enough, but let's just get an idea. Maybe that's something we can do more precisely in the coding, okay? Coding assignments. What we're gonna do is something like this. Basically, you may have some integer variable to say, let's say number of vertices, vertex visited, something like that, right? Let's say 0 to begin with, all right? And then you want to say something like while the number of vertices visited is strictly less, or you can say not equal to, doesn't matter. Okay, let's say strictly less than the number of vertices in the graph. Of course, you will have a way to really figure out how many vertices. It could be just an attributes, right? So this one tells you you're going to exit the loop as soon as it is equal to. That means exit the loop as soon as the number of vertices visited. Okay, I'll write a little better. Is larger than or equal to that. Of course, we're taking the equal to, right? That's what we're looking for. By the way, should you ever have a breadth search or depth search where the number of vertices visited is more than the vertices in the graph? What does that mean when you have that condition? Let me say the question again. What does it really mean when you do a depth search or breadth search where the number of vertices you have visited is more than the vertices in the graph? What does that really mean? Okay, go ahead.
Yeah, you just repeated a vertex, like counted it again or something.
Yeah, well, easy. That means your implementation is wrong, right? You shouldn't really get more than that, right? You want to recount or maybe fix your code, all right? So that's why we don't really talk about like a lot more than, right? So it should be just exactly equal to. All right, good. Okay, so inside the loop, of course, I'll let you figure out the details, but it will be something like, so here we are now in the loop. That means it's still strictly less than. So you have to pick some vertex. Let's say X. That's unvisited. And then start breadth search on X. Right? Of course, it is very important here inside this particular breadth first search, the number of vertex visited, this variable here, should be properly updated, right? Every time you actually have a discovery edge, you should increment this counter by 1, right? Properly updated. For every discovery edge that you mark. Okay, I'll just highlight it right here. All right. And of course, after this breadth first search, you got to go back to the while loop and check that counter until the point that you actually do it, you actually got it, so you will know you got all the connected components. All right. That's more or less what you have to do. Okay. So here we say that the number of iterations simply correspond to the number of connected components, right? Of course, we'll let you figure out the detail once you get to the eclipse, right? I think it's better to really, I think it's good, it's actually beneficial to kind of see how things should work conceptually. A little bit vague, that's okay. We're just thinking more abstractly. But we also want to build something that's going to work. So we're going to do some Java code, okay? We'll do that. All right, and let's move back. Okay, spanning tree. Okay, so I would say it's really as soon as you're done with the breadth first search, you get a spanning tree for that particular connected components. Okay, so each breadth first search will return, well, let's say, identify. For example, if I start from here, it's going to be the spanning tree for the connected components containing the start vertex A. Right? That's the way to put it. Okay, I'll write it down. Well, identify the spanning tree containing the start vertex, right? So for example, if I only start from A over here, I can only get a spanning tree for this particular connected components. That one wouldn't cover, for example, over here. That wouldn't, right? Because they're not exactly connected, right? Only for that particular connected components containing the start vertex. All right, and then is G connected? Well, you just got to see how many breadth first search you will need to do. If you knew exactly 1, then that means it's connected. Okay. How many breadth first searches are needed to cover all vertices? If it is 1, then it is connected. There's only a single connected component that's going to cover all the vertices. So the answer should be exactly 1. Right? So you can think about in this while loop over here, you will somehow have to see how many iterations we actually have to go in order to cover or visit all the vertices. If that's exactly 1 iteration, the graph itself is completely connected. Otherwise, it has at least 2 connected components. Right? Okay, hopefully that's clear. All right. All right, now, guys, let's talk about this one here. All right, this one's very interesting. Okay. So now, if the graph is cyclic, we want to return a cycle. Right? Here's the thing. Let's say a graph that's general. When I say general, it can be directed, can be undirected. Right? What we said earlier about the same kind of a question here for depth first search, I didn't kind of the example I put here apparently is undirected, but it also applies if the graph itself is directed. In which case, if you can see a back edge from depth first search, doesn't matter if the graph is directed or undirected, seeing a back edge means that you have a cycle. So now the question is, can we apply the same argument to breadth first search? Okay, I'll put a question here, first of all, to help us. But we're going to discuss this. Okay, so here, let me put down something here. So now, the graph, how about we do a table here? Okay, just to help you. This one is a little bit subtle, also tricky. So let's get this right. So the input graph can either be undirected okay, I think I definitely can write better. It's either undirected or it could be directed. All right, let's talk about two possibilities here. So here, another dimension. We're basically talking about, we're doing either we're having a back edge or we might have a cross edge, depending on what search we're doing. Okay, I'll write it down. So here, it could be either, so let's say a back edge is found. Apparently that means we're doing depth first search. Versus if a cross edge is found. That would imply we're doing breadth first search. Okay, now for 1, 2, and 3, and 4, all these 4, we're basically asking the same question. Is the graph cyclic? Does it have a cycle? Okay. That's what we are interested in knowing. So here, 1 here, 2 here, so 3 here, and 4 here, right? All these 4. We are basically asking the same question. Does there exist a cycle? All right. Okay, why don't we just go over the actual result, like a facts together, because it does require some thinking. I can leave to you maybe after the class, but let's now go over some ideas and also example, at least to convince you intuitively by gonna do some other work after the class. All right. So it turns out for depth first search, yes, and yes. Yes, in the sense that when you actually do the depth first search and then you identify some back edge, doesn't matter if the graph is directed or undirected. The fact that you see a back edge, you have a cycle. Okay, we'll see example in a moment. All right. What about breadth first search? That one's interesting. All right, for breadth first search. You know, for example, the one we did earlier, let's say here. So there is a back edge right here. The graph is undirected, and apparently this is a cycle right here. Okay, that one kind of justify one case. Okay. This one here, so let me just go back here. Yep. So here, this will be yes. If the graph is undirected, then you can say that finding a cross edge tells you that there's a cycle. Now the tricky bit is the final one. If the graph is directed and you find a cross edge, can you conclude that there's a cycle? Not necessarily. You cannot do that right away. Okay? Not necessarily. I'm not saying yes, there's a cycle. I'm not saying no, there's not a cycle. I'm saying not necessarily. There may be not, depending on how the arrows, like a direction, will go in the graph. I'll show you. All right? All right, so this table here is actually very important. We are basically comparing the two most fundamental search mechanism for the graph, depth first search and graph first search. And we talk about specifically about the back edge and also cross edge. We're saying that they work almost the same way, except when you say you have found a cross edge in the case of breadth-first search. And the fact is, if the graph happened to be directed, you cannot conclude right away definitively to say there's a cycle. That's the only case you cannot say for sure. Other than that, they work really the same way. Okay, similar. All right. Let's now try to look into this point, which is very important. Okay, let's now look into this point. Okay. At this one, I do apologize. I just modified this diagram a bit just during the break because I found that this might be a little bit better to illustrate. Okay, so it's a little bit different from the template you might have downloaded from the lecture slide. A little bit different. I just added one more graph. Okay. Let's now talk about. Let's go for depth-first search. Okay. So basically, we're asking, does a back edge in the case of depth-first search always imply there is a cycle, disregarding whether the graph is directed or undirected? So the answer is yes. It always implies. Okay. So this first question here is yes. But let's see some example to convince us right away. Okay. Let's now talk about the first one. Okay. So this will be Let's say this is the question we are trying to answer first. Okay. Let me do once more. Okay, how about this? Better. Okay. Let's now try to look at just these two. Okay, these two. And we're going to do depth-first search. Okay. So the first case, let's say the graph is undirected. And then I'm doing a depth-first search right here. Okay. So what we should really have is, well, here, let's see here. Basically, we are now trying to see how we can find a path that's going to lead to a back edge. That's what we're going to see. Okay. So let's now focus on what you want to focus on for the argument. Focus on finding a path leading to a back edge. Okay, that's the first one. Okay, focus on finding a path leading to a back edge. Okay, the first one. So one example one could be, let's say discovery A to B, discovery B to C, and then discovery C to D. Right? So far so good. Well, actually, as soon as we are here, you can see that for C, you just go back to A. Actually, that's a back edge right away. Right? So that one there is going to be a back edge right here. All right? So you can see the path leading to the back edge is A, B, and C. You got a cycle. Right? So this is a cycle. Okay. And then what if the graph is directed? If the graph is directed, you can think about the reason that you will actually lead to this particular back edge. The only way to go there, if you got direction, is when you actually got, for example, A to B. Otherwise, you wouldn't go that way, right? You got to go from A to B. And then you also got to go from B to C. Also, you go from C to A. It's got to be the way, right? On the other hand, let's say, for example, if I have the edge that goes like this, are we going to identify this as a cycle here? Not really, because in that way, you go from A to B and also B to C, and then for incident edges for C, yes, you do have like this one here and this one here and this one here. But for that one there, it's actually going incoming. So you don't really identify that as a cycle. Right? I'll write it down here. So this is a counter example you want to see. Right? So we go from here, A to B, and then B to C. Okay? So now you want to say that from here, the incoming edge will not be considered as a back edge. Because it's really incoming, you only consider as outgoing edges. It gotta be outgoing, and that goes to some visited node that will make it a back edge, but it's not the case. All right. So this one here is not a back edge. So if you follow the the arrow, and then you really lead to some unvisited nodes, that will guarantee you have a cycle, right? That's the main point. Okay. So that's for that first search. So this is not a back edge. All right, so now let's take a look at the breadth-first search, which is a little bit newer to us. Okay. Let's say the graph is undirected. Okay. So what we have is, so remember we're going to get A to B, A to B, A to C, and also A to D. All right, all good. A to B, A to C, A to D. And then that's a level one. And then here you can see that as soon as we get to B here, we can see there is a cross edge right here. Right? So that one also tells us there's a cycle because it's undirected. A, B, and C is a cycle. Okay, you got a cross edge. So this one here, this is a cross edge. So this cross edge implies there's a cycle. Cross edge, that means there is a cycle. All right. And let's now consider two cases, okay, for directed graph. One case, you will see that we may not have a cycle. The other one, we may have a cycle. Let's say this. Let me just put it this way. I'll just show you what this way. This is not a cycle. How about that? Let's say we have like this. Okay. So let's say this direction here, this direction here. You know, similar to the one we just did for depth first search. And then we just got that. Okay, a similar idea. Okay. So here, discovery, and then discovery, and also discovery, right? Discovery edges. So far, so good. And then you can see that right here, we actually got this one here. By definition, it should be a back edge. We do, right? However, this back edge over here, you can see we got this direction here. So this is not really a cycle. So having a cross edge right here doesn't really mean we have a cycle. Okay. So this is a cross edge. May not be a cycle. Okay, I think this diagram should be enough. Yeah, think about these two questions over here, maybe on Wednesday when we come back to here, and then I can do a recap again, just to summarize. But the main thing is to really look at this table here and to really remember, whenever you're doing a depth first search, as long as you can somehow follow the path and then find some back edge, you guarantee you have a cycle. Doesn't matter if the graph is directed or not. However, in the case of the Bradford search, finding a cross edge doesn't really mean you have a cycle. For example, here you can see we have found a cross edge, but there's no cycle as far as this part is concerned, right? So it's not necessarily always the case. Okay? Think about this property here, and then we'll try to recap, and maybe potentially a little bit more example just to show to you. Okay, okay, we got about 5 minutes. Let's now leave the Bradford search here, and I would like to talk about a second implementation strategy for graph. Okay, maybe just a little bit. Okay, just go over maybe some code structure in Java, and then we can look at the visualization on Wednesday when we resume. Okay, about 5 minutes. Okay, let's now take a look at right here. Okay, Bradford search about a graph question we just spoke about. Okay, adjacency list. Okay, so I'll try to make it not so much inheritance. You know, when I release the starter code for assignment number 2, I'll try to collapse everything you will need for the vertex into a single vertex class. So you can expect that there will be a package called adjacency list graph base in the assignment 2 starter code, right? But conceptually, you want to think about many of the stuff that you used to get from edge list graph, they are still there in the adjacency list. In some ways, it's more like an extension. Okay, so let's see. Okay, basically now the main extension is right here. Okay, I think one of your fellow students during the tutorial was wondering, why don't we actually store the incident edges in each vertex? There you go. That's one of the reasons why adjacency list is more common than edge list to really do the graph implementation. But it's still, people still use it. So that's why we still talk about it. All right, so why don't we just go directly to the Java classes very quickly, okay? And then we'll dive into details on Wednesday, okay, quickly. Let me now start with maybe the vertex over here, okay? So conceptually, we are really getting 3 classes in the context, okay? So we got vertex over here, the basic one, which has the elements for the vertex, right? That's why we got V, the generic parameter, okay? And also, based on what we learned earlier about edge list graph, so we also got something called edge list vertex, which store a DL node, doubly linked node, the position back to the list of vertices, right? That's something we had earlier. So this part here still remain the same. So to really create a vertex for the adjacency list vertex, so you can see that we have this class right here, adjacency list vertex. That's a new class. That one there basically has a storage of incident edges. It's going to be a doubly linked list. Each node stores the adjacency list edge, which is an edge class we're going to declare. Okay? So the small extension, but quite a fundamental one, is in the adjacency list graph, we actually got a doubly linked list of the edges, and those edges correspond to the incident edges for that particular vertex. Okay, we'll see some visualization later. Okay, so that's about vertex side. What about edges? Okay, if you recall, from the edge list implementation, we got edge here, we got element for the edge, we got origin, we got destination. Okay, we keep that. And also for the edge list edge from before, we also got the doubly linked node and the position back to the edge list, so we can remove it in a constant time. So we'll keep them. So now this is the thing. We got adjacency list edge. We introduced 2 things. One is about the origin incident edges list position and destination as well. So this is to say, whenever I want to remove a single edge, I have to go back to the corresponding incident edge list for that particular vertex and then remove them from there. Okay, we'll see exactly how this will work. Okay, so this will be for efficient. So these 2 are also very important. For efficient removal of edges. Especially since now every vertex stored their list of incident edges. When we remove a particular edge, we got to make sure we remove there from the corresponding vertices. Okay, so that's so these two are really the extension we have to understand. One is about the incident edges at each vertex. Okay, and the other one is about the extra 2 positions for each edge that we are storing. All right. Okay, I would say we stop here. You can take a look at the Java code, but when we resume on Wednesday, I'm going to recap about what we just said about the property for depth first search and breadth first search, the cross edge and back edge. And then we'll do some visualization of this. And then we'll go for a weighted graph. All right, thank you. See you on Wednesday.